In this lesson, we will change around the parameters in our code cell and see how changing these parameters influences the corresponding p-value, and thus which conclusions we can draw from it. Now, we can start with just the parameters that we had. In this case, the difference in population means is 30%, a mean of 1 for population 1 and a mean of 1.3 for population 2. Now, our sample size is 15 data points for each sample. We compute the mean for each sample, which are these vertical lines, and this of course will give us a mean difference, which is visualized on our distribution of sample differences with this red line. Now, each time I rerun this cell, we will see that we will get a new sample. And a new sample means will result in a distinct difference in means. And therefore, each time I rerun this cell, this red line here will shift around on our histogram. And also keep an eye on the corresponding p-value. So if I run this cell over and over, then we see that we indeed get different samples, different sample means, and thus a different difference in sample means. Now, for instance, in this case, we see that our observed difference falls within the blue region, and therefore this difference is not extreme enough to reject the null hypothesis. So from this sample, which is the only data that we're given in reality, we cannot conclude that there is a difference in population means. Therefore, in this specific case, with these particular parameters, the p-value will lead us to a wrong conclusion. But that's okay. Statistics is not about being right all of the time, just most of the time. Because if we run this cell again, for instance, then we see at some point that we do have an observed difference that falls in this red region. And thus, it is part of the 5% most extreme data, which is extreme enough for us that we reject the null hypothesis. Therefore, this particular pair of samples will have a difference in sample means that is sufficiently large for us to conclude that there is indeed also a difference in population means. Now, if we scroll up, then we see that for this particular pair of samples, the difference in mean is indeed minus 0.43. And this is even larger than the difference in means of the underlying populations, because for the populations, the difference was 0.3. So we see that a difference of samples that is larger than the difference of population means will lead us to conclude that there is indeed a difference in population means. We see that our manual p-value is 0.01 and the built-in p-value is 0.02. So this is still quite a large difference. And this comes from the fact that we made this approximation that this distribution is a normal distribution and not a student's t-distribution. However, at a later point in this lesson, we will increase the number of sample data points. And mathematicians have showed that if this number of sample data points becomes sufficiently large, then the student t-distribution will become a normal distribution. And thus, we expect that these two p-values will become much more equal to each other. So if we run this cell over and over again, and keep track of this red line, then we see that sometimes it will lead us to reject the null hypothesis and make the right conclusion, but sometimes it will still fall within the bulk of the histogram, leading us to conclude the wrong conclusion, namely accepting the null hypothesis. Let's change some parameters now, just to see how we can make it so that we will always make the right conclusion. And the first thing that we will do is we will change the underlying population means of our populations. Let's say that they're not different by 30%, but by 300%. So population will now have a mean of 3 compared to 1 for population 1. So if we run this cell and we leave all of the rest the same, and we look at our histograms, then we see indeed that it's very clear, even from our sample histograms, that these come from different populations and thus with a different population mean. And this is also very clear when we look at our distribution of sample means. Now, this clearly shows that this distribution that we use is based on the null hypothesis, meaning that the difference in means of the underlying populations is 0, because clearly our difference that we find for our specific samples lies way out on the left of this distribution. And thus, there will be almost zero values of this distribution that are more extreme than this observed value. And thus, the corresponding p-values, they are indeed tiny. And the way to see this is to look at this e minus 36 and this e minus 12 at the end of this number. This indicates the number of zeros after the decimal point. So this will be a 4 with 36 zeros in front of it. So a very tiny number, basically 0. Now we see that this is a very robust result, because if we run this cell over and over again, then we will see that each time our observed difference, so the red line, will lie well outside of the blue range in our distribution. And each time the corresponding p-value will be incredibly small. And this leads us to conclude that even though our sample data sets are very small, only 15 data points for each sample set, if the phenomenon in the underlying populations is so large, then the p-value will always get the right result. But this of course isn't that surprising, and it doesn't give us anything new, because we could have gotten to the same conclusion that the population means are different from each other just by looking at the sample histograms. If I rerun this cell over and over, and now we focus on the sample histograms, then there is not one scenario where we would not conclude that these samples indeed come from different populations. So let's change our parameters then to make it again much more interesting. Let's again decrease the difference between the population means. And now let's decrease it such that it's only different by 10%. Let's see if our p-value correctly identifies this difference based on a sample of only 15 points. So if we scroll down again and we go to our figures, we indeed see that the population histograms are almost overlapping, which indicates the fact that they are of course only different by 10%. However, it still allows us to look at these histograms and conclude that they are indeed different, which is of course absolutely not the case by looking at the sample histograms. So then we look at our p-value. We see that this difference in sample means, which is 0.099, falls within the bulk of this distribution, meaning that based on this difference of minus 0.099, we cannot conclude that there is a difference in means of the underlying populations. And therefore, the p-value, which is roughly 0.55, leads us to the wrong conclusion. Now, if we run this cell over and over again and keep an eye on this red line, let's see if sometimes it falls within this red region. And we see here that it just not makes it. So if we do it over and over again, then we sometimes get indeed that a red line just falls within this region. Therefore, we see a p-value of 0.04 for our manual p-value, but 0.06 for our built-in p-value. So it's really just at the edge of this extremity interval. Therefore, we want to get something more extreme. So let's run this cell over and over again, and let's hope that at some point we will indeed get a value that is inside the red region. Now, as I'm going through this, you clearly see that in the vast majority of the times, we do get a value that does not reject the null hypothesis. So that leads to the wrong conclusion. But then, just as I was saying that, we do get a value that is quite far in this red region. And indeed, the p-value is roughly 0, but also for the built-in p-value. So here we're quite certain. So why is it that then in this case, we do get a p-value that allows us to reject the null hypothesis? Well, let's look at the actual difference of our sample statistics. In this case, we got a difference of minus 0.468. Now remember, the population difference was only 0.1. So we have a sample difference in means that is almost 5 times as large as the difference in the underlying populations. And therefore we can say that we have a very unrepresentative sample of our populations. And this is the only reason that we all of a sudden have a p-value that allows us to reject the null hypothesis. Indeed, if we look at the boundaries here that indicate when we want to reject the null hypothesis, which in our case corresponds to a statistical significance level of 5%, then we see that we can only reject the null hypothesis if we get an absolute value of the difference in means that is larger than 0.277. Now this means that we would only be able to identify this difference in population means if we would draw samples that had a sample mean difference that is 2 times or almost 3 times as large as the population difference. And this just shows that you wouldn't want to draw any false conclusions from sample data about the underlying populations. And thus in this case, the p-value allows us to be prudent. And this becomes even more apparent when we indeed make this difference in population statistics even smaller. In fact, let's just make them equal. Therefore, in this case, we have the scenario where we draw samples from populations that are indistinguishable from one another. So let's see how the p-value handles this scenario. So if we run this cell and we indeed look at our population histograms, then we see that they are indeed equal to each other. And also the samples that we draw have a mean that is very close to one another. In fact, the difference in mean is only 0.044. So let's see what our p-values say. Well, we clearly see that this observed difference in sample means lies well in the middle of our distribution. And again, this distribution represents the null hypothesis, meaning that this is the right distribution if our underlying populations are identical. And in this case, they are indeed identical. So we know for sure that this is the right distribution. And this corresponds to a p-value of almost 1, the maximum p-value. So 0.83 for the manually computed p-value and 0.84 for the built-in function, meaning that roughly 84% of all of the data in this distribution is more extreme than our value. So we didn't get an extreme value at all. And thus in this case, the p-value allows us to get to the right conclusion by not rejecting the null hypothesis. So if we run this cell over and over again, then we do see indeed that most of the times, I was going to say most of the times it would fall within this blue region, but then sometimes still it falls within the red region. So meaning that we falsely reject the null hypothesis, and thus we get to a false conclusion. Now in this case, we get a p-value that is quite low, meaning that we would confidently reject the null hypothesis. Now let's see why this is. Well, it is because we get a non-representative sample. Now clearly, we see that the difference in means for these two samples is very large. In fact, it is 0.529. Now this is incredibly large if you think that the difference in means of the underlying populations is 0. Now it's very good to have this come up in this lecture because actually this is incredibly rare to come up, but it still shows that in statistics, even though you make all of the right choices, you might sometimes end with false results. If in reality you were indeed given this sample, then it would be indeed the right decision to say that this sample shows that there is indeed a difference in underlying populations, because in reality you wouldn't know that you've gotten a very unrepresentative sample. But in the long run, if you have a long career as a data scientist, you will see that most of the times you will get a sample that represents the underlying population well. And thus for most samples, you will fall within this blue region. And this also shows the strength of the p-value, meaning that even if you get a sample which clearly has a difference in means, that doesn't mean that you want to conclude that this difference in means for your samples also relates to a difference in means of the underlying populations. In fact, in most cases in this scenario, the p-value actually corrects us in thinking that this difference in means would be any significant. And this of course shows the strength of the p-value. Now, I've run this a couple of times now, and we see that indeed most of the times it will be in the bulk of this histogram, giving us the right conclusion. So now let's address the annoying fact that this manual p-value that we computed is always a bit different than this built-in p-value. In this case, it's even notably different, so it's 0.19 for the manual p-value and 0.22 for the built-in p-value. We can address this with the same change that also reduces the chance significantly of getting these very non-representative samples, as which we saw earlier. And in fact, this change will be the strategy that will always be the best strategy. And by now you know, it's to collect more data. And for our simulations, we can simulate this collecting of more data with increasing the sample size of our sample datasets. Up till now, we only worked with 15 data points for each sample set. So if we do this times 10, so that we have 150 data points for each of our two sample sets, then we will see the following happen. If we scroll down and we look at our graphs and our p-values, then we see the following. First of all, we see that our sample histograms are starting to look a little bit more like our population histograms. They show faintly this bell-shaped curve. And also because we have much more sample data points, the chance of getting a very unrepresentative data sample have reduced significantly. And now also, most importantly, we see that our manual p-value is much closer to the built-in p-value, which means that our approximation that this distribution is a normal distribution is much more accurate than before. And this is also what mathematicians found. Increase the sample size and this t-distribution will resemble a normal distribution more and more. Now, if we run this cell over and over again, then we will see that we will almost never encounter a false rejection of the null hypothesis, meaning that our specific observed difference in means will almost never fall in these red regions. And indeed, the p-value will never drop below 0.05. Now, of course, I say this and then all of a sudden I get such a value, but I am quite confident that this is not the case because we indeed have a sample set of 150 points, which makes the results much more robust. So now that we have a much larger sample size, let's see if this sample size allows the p-value to indeed spot a small difference in population means. So let's again change it to a difference of 10%. So let's see what the p-value then says. In this case, we see that indeed the p-value is right at the edge. In fact, it is, well, just 5%. So in this specific case, we might still reject the null hypothesis that these two populations have an equal mean and just get to the right conclusion. So if we run this over and over again, then we see that sometimes we still do not reject the null hypothesis and thus get the wrong solution. However, we see that in some cases, we of course do reject the null hypothesis and get to the right conclusion and thus detecting this small difference based on our sample. So if we run this over and over again, then we see that most of the times we will be in this red region. And therefore, most of the times, we will indeed reject the null hypothesis and get to the right conclusion. Now, this was not the case in the scenario where we had 15 data points. So we see that increasing our number of data points will increase the robustness of our statistics. Now, to finish off, let's reduce the difference between our populations even further. Let's say, for instance, to 0.05 difference, so 5%, but let's increase the sample size even more to 1,500 samples and see if the p-value is able to detect such a small difference. So if we scroll down, then we see indeed that the p-value is indeed smaller than 0.05. And thus a very small difference in populations is detected as long as we have a large enough sample. So here our sample is so large that indeed our histograms look a lot like those of the population ones. So if we run this over and over again, then we still see that a sample of 1,500 is not large enough to always get to the right conclusion. If we run this over and over again, we still see that sometimes we do get a very definite conclusion, but sometimes we also don't. And this is very typical for statistics. And it's worth repeating again. Statistics is not about being right all of the times. It's just about being right in the long term. If you have to do many of these examples and these experiments, then if you keep to your statistics, then you know that in the long run, you will be right most of the times. So let's now leave these simulations behind and go to the next lessons, where we will learn about the specific statistical tests that apply in specific scenarios, which will be very practical and hands-on knowledge that you will be directly able to implement in your own work stream.